Hello everyone. Today let us discuss about principal component analysis. This is one of the important algorithm in machine learning. So this is used for feature reduction and also for use for classifications. So there are few set of algorithms that we have to look into this. So one algorithm what we need to know is about the eigenvectors and covariance. So those videos I have already presented in my basic videos. So we can please check those videos. I have given those links in the description, and I also given the references and also the link for this code. Now if you look into this, so I have added MATLAB, NumPy, Pandas and sklearn libraries. These are some of the libraries which is useful for our tutorial. So using pandas, so what I did is I have downloaded this iris data, and I have defined the columns with the following names. So I can change the column names what I want, but that is not necessary for right now. So later on what I have done is I am trying to remove if there is any null rows. I have removed those null rows, and I was checking the data. So if you keep use this tail function, it should display the data which is in the bottom of the bottom row of the section of a given data file. And if you use head method, so it will display the header section, I mean the top 5 rows of the data. So this data what I'm doing is I'm separating it into two pieces, x and y. So x for all the input values like length, width, petal and width, and y for the classes, so type of the flower. Now here what we are doing is we are classifying the flower basing on the dimensions, basing on the inputs we have received it. So we have four dimensions here. Now if you want to plot a graph, you can plot a graph with 2 dimensions. It's very easy to plot. Now if you want to plot a graph with 3 dimensions, it might be a little difficult, but it's we can do it. Now it's very difficult to do a graph with 4 dimension and 5 dimension. Of course we can do it using heat map and some other graph, but it's cumbersome to understand it. So this PCA will help us to reduce these many dimensions into another subspace, into another sub feature. Now let us look into this. So I have divided the data in terms of x and y, x for the input and y for the output. Now I am doing scaling here. So scaling is one of the important process. For example, you want to know the mileage of a car. For example, like for 1 liter of the fuel or a unit of, let's say, 1 liter is the machine is running up to 10 kilometers. Okay, that is fine. So what if I change from liters to milliliters? Now I will say like this: 1,000 milliliters of petrol or gas is used to run for 10 kilometers. Or let's say I use liters as instead of milliliters, I use the liters, and kilometers I use some meters. So what I say is for 1 liter of gas, this car run up to 10,000 meters. So what is happening here? Because of the dimensions of because of different scaling and metrics, the data is skewed. It doesn't make any sense. It doesn't give any sense for one dimension to other dimension to compare with one dimension to other dimension. So that's why we use scaling. So scaling, what we'll do is it will analyze the entire vector. It will check for the maximum value and minimum value and find out the mean. And it will, with respect to that value, it will gives us the value between 0 and 1. So you can see this. So so all are in decimals. So e power 0 1, so you can see it's like 0.09 something like that. So like this, all this particular data set is being converted into standard scales, so that it makes sense to compare with one dimension to other dimensions. So this is what we do with scaling. Now we have to do a covariance matrix. So how we do covariance matrix for PCA? So first what we do is we will have this mean vector. So mean vector, here we are calling the numpy mean method, and we are using the axis 0. So what we are trying to do is we are getting the mean of individual columns, and then we're getting the mean, and we are separating from the standard vector which we have scaled the matrix, and then we are transposing it, and then we are again multiplying with the same set, x standard minus mean vector. And this entire magnitude is divided by the sample space minus 1. So what is sample space? So sample space is nothing but the number of data points. For here you can see in the head, you can see the 5 rows. So these 5 rows are nothing but the data sample space. So here what we are doing is, we have this variable called shape for numpy arrays. So when we do that, we can see that the size of the array is 150 by 4. So 150 is the sample space. So we are subtracting 1 from the sample space, which is the standard method, and we are getting the covariance matrix. So this is the covariant matrix that we get. So instead of doing this formula, we can use numpy covariance matrix, and when we use this formula, we can also get the same covariance matrix. Earlier in my basics tutorial, in order to mention the relationship for one dimension to other dimensions, this is how we will get the heat map. Right now we don't need a heat map. This is just for demo purpose to show how we can use the heat map. Heat map mostly we use it for covariance matrix using Seaborn library. Now, the next step, once we get from the covariance matrix, we will find out eigenvectors and eigenvalues. So I have covered certain basics for eigenvalues and eigenvectors in one of my previous basic tutorials. I'm going to do deep dive for those eigenvalues and eigenvectors in the future lessons. So here you have to identify that we have eigenvectors and eigenvalues, and you can see this particular eigenvalue is corresponding eigenvector here. So the first eigenvalue is corresponding to the first row of the eigenvectors. So once we get this eigenvalues and eigenvectors, what we do is we'll combine them. We'll combine both of them, so that we can sort these vectors based on the magnitude of the eigenvalues. So here, before that, here we'll verify whether these eigenvalues are accurate or not. In order to verify the accuracy of eigenvalue, so what we do is, we will square this eigenvalue and add it to the square. So we square each individual elements and we'll add it, and we'll find out whether the sum is equals to 1. So we'll see that we'll get the sum as 1, so it means this is the proper eigenvalues. So now what we do is we do pairing. So as I mentioned earlier, we'll pair eigenvalues with corresponding eigenvectors. So there are multiple ways to do it. So this is one way to pair the eigenvalues with eigenvectors. So we'll get some sort of this kind of an array. Otherwise you can use for loop like this, or you can use short form like this. So either way we'll get the pair as a matrix, and then what we'll do is we'll start sorting it. So if you see here eigenpairs, we use this sort function to sort it, and then we do reverse it so that we can have a descending order from increasing to decreasing value, something like this. So it's so that we can identify what are the vectors which is corresponding to highest value to the least one. So once we get that one, so what we'll do is we'll try to see what is the sum of individual values, sum of all the eigenvalues, and we divide with the individual eigenvalues, so that we will know what is the variance. So variance means how much this particular eigenvector is showing the variation in the data. So this is showing around 72%, this is showing around 23%. So if you add all three of them, it accumulates to 100. So it means all the eigenvectors which corresponding to these eigen values constitute 100% of the data. But if you observe, if we add the first two eigenvalues, it's constitute 95 percentage of the data. So it means these two vectors hold 95% of the data. So we can focus on two dimensions, this particular two sub-feature phase, so instead of four original dimensions. So what we'll do is, in order to get these new dimensions, so we'll stack these two eigenpair vectors. When we stack these two eigenpair vectors, we'll get this matrix. So with this matrix, we'll multiply with the actual standard X matrix, which is the input matrix, and we'll get the we'll get all the X values corresponding to principal component 1 and principal component 2. So this set of matrix 4 dimension matrix is now converted into 2 dimension, you can say kind of a hybrid matrix, something like this. So it means we have converted a 4 dimensions into 2 dimensions. Now it is easy for us to analyze. If you Now what we are doing now is we are attaching the y, that is the output, the classification, to this particular data frame, and we make it as a final data frame. So if you see the final data frame, we have principal component 1, principal component 2, which are the two new dimensions, and along with the classification, the species. So now you can see with this 2 dimension, it's easy to plot the graph, and we can easy to classify, so that which corresponding to which principal vector we can identify which what is the species of the flower. And not only that, using the skill and library, we can directly call this PCA class, and then we can perform this particular fit transformation, and we can directly get principal components 1 and 2, just like the above. So instead of following all this procedure, we can directly call this PCA method of the skill, and we can have this particular matrix. And then we can attach the output for this particular data frame, and then we can plot the graph, something like this. So this is about PCA. So this is about feature reduction and classification. Thank you for listening.